Hello everyone. It's 12:01, so let's start. Welcome to the CGS SOS online lecture event for the month of November. Hope this will be the last virtual event before we heading to our in-person event for December. Today's talk will be working with sensitive clays, the Norwegian experience by Jean-Sébastien Laurent. He is the head of Office of Norwegian Geotechnical Institute, Trondheim, Norway. So we'll briefly introduce him after we go through few slides and few announcements and for this talk and the upcoming events. So we'd like to thank our sponsors, of course, for their generous support, EBS, Geostructural, Grounded Engineering, GeoSolve, Tharver Engineering, Contact, GeoSyntech, Keller, Golder, and Duidec. Thank you all for your generous sponsors and cooperation. Christmas dinner. So we are very excited for going back to in-person event, which will be the Christmas dinner on December 8th. Hope you guys already started getting the email from CGS SOS and from Eventbrite about this event. So make sure you registered for this, and our guest speaker will be Riley Bedo from RMIT, I believe. The topics will be interesting. Also, how the climate-driven permafrost degradation will impact infrastructure in Canadian's north. So we are very excited about to go back to in-person event in Christmas, and also would like to hear from Riley. So for Christmas dinner, as it will be an in-person event, there are some restrictions in terms of COVID-19 rules, and there will be tickets available, but there is a cap on the tickets for that venue. There is a 200 is the max limit for the in-person gathering, probably for that venue. The costing for the regular registration will be $110 for the CGS and the government members, and for the non-CGS members will be $125. The student cost is very minimum, $20 only, but there is only a limited number of tickets for the students. So whoever the students would like to join this event, feel free to register soon as possible. There will be evening program in that event, women in CGS around 4:30, and then followed by cocktails and socializing at 5:30, and then dinner will be served at 6:30, and the lecture will be at 7:30. So keep an eye in your mailbox from the email from CGS SOS, and hope we will see you again in person in that Christmas dinner event. Just to make sure that that event will be, say, in person, so there is a vaccine passport requirement for the attendees. So make sure that you brought your ID card and the vaccine passport to get into the venue. Okay. So as I said before, our today's talk will be working with sensitive clays, the Norwegian experience. Before introducing John, I would like to share a very brief here and acknowledge the person who helped me to introduce John, and also to get this event. Few months back in CGS meeting, when he discussed about a lecture on sensitive clay, I kind of reached out to Susan Lakas, another great lady and in this field. And thanks to Susan, she introduced me to John in Norway, and like working. This is my favorite topics also, because I'm also working on this field for more than 10 years. So I'm very excited to meet John and Susan and finalize these topics for our today's event. And we'll be more than happy to have this event in person. But since John is in Norway, so because of all the restrictions, we have to have this event virtual. But hopefully next time we can have event with John in person in Canada. So briefly, John is a senior scientist and head of section at NGI office in Trondheim. He completed his Bachelor of Engineering in Engineering Geology from Laval University in Quebec City in 2003, and then completed his Master's from University of Oslo in 2005, and then finished his PhD in Geotechnical Engineering from Norwegian University of Science and Technology in Trondheim in 2009. He is a chairman and co-chairman for several international workshop and symposium, including first and second international workshop on landslide in sensitive clay in 2013 and 17, and first international symposium on geotest sites in 2019. He is a lecturer at Norwegian University of Science and Technology in Trondheim. He contributed to Norway's national technical guidelines on landslides in sensitive clays. He also authored and co-authored over 120 scholarly papers. So without further ado, let's join me and welcoming John from Norway. John, it's all yours.
Well, thank you very much for the very nice introduction. And it's a pleasure to be here this afternoon for you guys. And thank you very much for the invitation to present a bit of our experience with Norwegian clays. I think this is a really interesting topic, and I look forward to giving you some examples of what we are working with. Now I'll just try to see if I am sharing the right screen. This one. Could you acknowledge, Rajib, that you're seeing my
yeah,
presentation?
I can see the screen with working with sensitive clay with your title cover page. Yes.
Perfect. Thank you. Then I think we are good to go. Yeah. So thanks again for the invitation, and I think it's a pity that we're not able to have this event and physically back everyone in Ontario. It would have been really nice to meet all of you and maybe grab some dinner and a beer afterwards. It would have been really nice to share some experience, but we'll have to keep that for next time. As I said to Rajib, I'll be having a sabbatical year next year, working from Ottawa, so there will be some more opportunity, I'm sure. Maybe just before we go on with the topic of sensitive clays, I just want to show a little bit where I'm from. I'm actually not so far from Toronto, where many of you are probably sitting today. I'm from a small town, small village called Fort Coulanges, 100 kilometers north of Ottawa. I have to be careful when I say that, on the right side on the map on the Ottawa River, or on the east side. It may be a bit misunderstanding if I say the right side here between the French and the English. But I've been living there I was born there and raised there. My father was a lumberjack working in the timber industry. And then later I did my studies back in Quebec City before I went to Norway, where I was supposed to be in Norway for just a semester as an exchange student for 6 months. But then I've been here for 21 years now, so time goes really fast. Today I'm living in Trondheim, that's in the middle part of Norway, in central Norway. Just to show you, if I go back, Trondheim here in the middle part of Norway is the same latitude as the Nunavut and the Northwest Territory, so it's pretty high up north. This is a picture of my family. I have two boys. My wife is there with a traditional Norwegian suit that they use when it's special occasions. So this is very traditional. As you may know, Norway is a country that is quite good at cross-country skiing, but this is not really my sport, but my family does it quite a lot. But I try to bring to my kids a bit of the Canadian experience, and I built this hockey rink just besides my house every year, and the kids can play hockey, and we try to have that. And I'm also try to put my kids cheering for the right team. So you guys in Ontario, you probably remember the playoffs last year with the Canadians beat the Toronto Maple Leafs. I'm sure you'll agree with me that this is the right team. So I think we just have to close the chat because I don't want to discuss about this year's situation. So that was a bit about me. Now I'm working at the Norwegian Geotechnical Institute. We are situated in Norway. Yes, we are an independent international center for research and consultancy in engineering-related geoscience. So everything within geotechnical engineering, geological engineering, geology, geophysics. So we do a lot of multidisciplinary work. And our mandate is simple: is to try to find and develop sustainable solutions for infrastructure, both on land and at the sea, and within environmental technology, contaminated soil, natural hazard such as landslides and avalanche. So our research is really to find some practical solutions for some of the most important challenges that the world is facing regarding climate, environment, energy, and natural hazards. So these are actually the four sections that we have at NGI. So locally and globally, in Norway, we have three main offices. The main office is in Oslo. We have a small research station in Stryn that is working quite a lot with snow avalanche and these type of problems. And then we have a smaller office in Trondheim, where we are at the moment nearly 25 employees, quite close to the university, where we have a close collaboration with the Research Institute in Geotechnical Engineering here. At the moment, we are 325 employees totally at the NGI, and with representative from 39 different nationalities. So it's pretty multicultural. We also have offices in the US, in Houston, and in Australia, back in Perth. And we have close collaboration with many universities all over the world. This is just a slide showing some of the examples of projects we're working with NGI. So everything from the offshore energy to natural hazard offshore. On land, we have tunneling, lots of different types of projects. And one thing that I work quite closely with is this aspect of quick clay landslides, which brings us to the topic of the presentation today. When I first met Rajib this summer, he was asking us if we could present something about our work that we do with sensitive clays in Norway. And this is a very important, but also very wide topic. There's a lot of things we could focus on in the presentation like that. But what I was thinking of is that I'll start first with a background, and then I'll go shortly with what are the causes for landslides and sensitive clays and the type of mechanisms that we observe, maybe with some of the differences that we see between Canadians landslide in Eastern Canada in sensitive clays and the one we see in Norway. Furthermore, I'll say some words about some of the methods that we use today for the detection of quick clays. Some of the works that we do on hazard and risk assessment. This is quite important. And then I'll say something about both the pre-failure, failure stage, and the post-failure behavior of quick clay landslides. Also, a little bit about the design parameters that we use when we look at the failure stage and the slow stability parts there. So if we start, what is a quick clay? I think the terminology is not really used in Canada. In Canada, we use mostly the term sensitivity, and we say sensitive clay depending on what the sensitivity of the clay is. And there are many different scales of sensitivities that can be used in Eastern Canada or Western Canada, depending where you come from. In Norway, when we refer to a quick clay, this is a very strict definition. It is a clay that has a remolded shear strength that is less than 0.5 kPa. Also, if you look in Sweden, you know, the Swedes and the Norwegian, they make a lot of jokes from each other. And the Swedes, they have a little difference here. For when they call it a quick clay, for them is a clay that has a remolded strength less than 0.4 kPa. I'm not sure where the difference come from, but those are small differences that is important to know when you deal with this material, and try to, for example, compare some of the data that we share. But in the clays that we have, many parts in eastern Canada and in Norway or all of Scandinavia are pretty similar from a geological point of view. What happens is that these clays, these marine clays, were deposited in a salt environment in the sea for many thousand years ago. And then when they were deposited there, they because of the salts in the seawater, the clay tend to flocculate. And then you have these salt ions between the clay particles that will build some electrochemical bridges between these particles. And with time, because of the relative fall of sea level in the northern hemisphere, these clays will emerge from the sea. And then at the time, the clays will be subjected to a leaching of by the fresh groundwater flow that will remove these electrochemical bonds between the particles. That is leading to a sort of a metastable structure. It's an open structure without the bindings between the particles. So then when you start, for example, shearing these clays, and you start remolding them, they will behave a bit like a soup, or like ketchup, if you want, very liquid behavior. Here is just an example of where we find pockets of leach clay for typical Norwegian conditions, and it's due to the fresh groundwater flow in the ground. So you can have flow of water through fissured bedrock, through the moraine material and the tills, but you can also have fresh water coming from precipitation, and then you can leach the clay on the close to the surface, but also at greater depth. Norwegian conditions are such that there's a lot of small sedimentary basins with many fjords, and the situation are different from one place to the other. So a lot of work in Norway is done to try to detect these quick clay pockets. When it comes to quick clay landslides, there are different typical triggering mechanisms to start landslides like that. The main ones, I mean, we can divide them into natural type of triggers and man-made triggers. So the natural ones, usually we're talking about river erosion in a creek or in a river. It can be from very intense and long-lasting rainfall, and even earthquake is known to have triggered quick clay landslides. On the other side, when it comes to man-made trigger, we have a lot of experience with that, unfortunately, during the last years. And it can be different elements that lead a slope to failure. Some examples can be loading a slope at the top with an embankment or a fill that will create or start a sort of a progressive failure along a critical slip surface. It can be also excavation at the bottom of a slope. It can be blasting and so on. So there are many different type of triggering mechanisms. But what we see is that quite often it's not only there's often several reasons why a landslide has occurred. So we can have some preconditioning factors, and then you have one trigger at the end. So it's often not so easy to pinpoint which element was the one that really led to the failure. In terms of landslide mechanisms, what we observe in Norway is that when there is quick clay in the ground, most of the landslide tend to be a type of flow slides that we often refer to in Canada, or retrogressive landslides. So you have a landslide starting with some potential erosion along a creek. You have an initial landslide, that leads to this open crater, and then the slope process will go backwards, and the crater will be bigger and bigger. This, I would say, is most likely around 80–90% of the slides that we observe here in Norway. If the slide doesn't go deep in the quicklay, if the quicklay is very deep and it's mostly superficial, quite often what we'll see is a type of a rotational type of landslide. So these are often associated also with human activity and other processes. The flake type landslide, this is not often seen in Canada, I think. And the reason for that is that it's probably because of the geology as well and the type of clays that we deal with. But what we see here is that when we have thin layers of these very sensitive or quick clay, and it's a layered soil, often we can have these sort of a flake type landslide. They look a bit like a sort of a dry snow avalanche. So you have a flake just going down the mountainside or on the ground. So we see them quite a lot. In Canada, that would be more type of a spread failure, where we have these horse and graben. The problem here is that the flake will run, will go downwards, and then it won't spread with horse and grabens that like we see in Canada. So if I compare to Canadian cases, there was a paper by Denis Demers and colleagues back in 2014, and the overview that they have from Eastern Canada in Quebec, they had looked at 108 cases of historical landslides, and 58% of them were flow slides, 37% spreads, and 5% they were difficult to say what type of they were. There was other types, but we see that spread failures are quite often happening also in Canada. Maybe one of the best examples to show some of the large Norwegian historical landslide is the Risa landslide. This example, I'll try to here. I have a little video. I'm not sure if it's working. The Risa landslide occurred back in 1978, and it's a good example of landslide showing that various mechanisms can be involved. The first part of this landslide actually occurred along the lake bottom, where the farmer put a little fill along the shoreline, just at this emplacement there. So it's a small fill that was 200 cubic meters. So it shows that a small change in stress condition can have very high consequences on the slope here. So the initial landslide retrogressed for nearly 40 meters in this area here, and it took nearly 50–60 minutes to develop. After that, there was a larger landslide that developed in this region. Also, it took nearly 40 minutes to develop. But when this flake went into the lake, that opened really the crater for the rest of the soil to come out of the ground, and the sliding process continued upslope, and it retrogressed for more than 1.6 kilometer from the lake. So this distance here is nearly 1.6 kilometers. So it's a very large landslide, and a total of 6 million cubic meters. But it shows again how gigantic it can be, just because of a very small field that was put in place at this region. Earlier last year, in June last year, there was another quite amazing landslide that occurred in northern Norway. That landslide in Alta took 8 houses and led to very important damages in this region. It was a good thing, however, that no lives were lost. Let's see. Yeah, no lives were lost there, but the video that was captured there is quite remarkable. I'll show that with on YouTube here. I hope it's working. Let's see. I'll just try to pause that for a few seconds. This video here, there was the man that owns this white house there. He came back from work in the afternoon of June the 3rd. It was around 4 o'clock, and then he was going to grab a beer. Actually, we talked to him in the aftermath of that landslide. He was going to grab a beer and then going to work on this patio, this veranda that he was building. And then he registered some cracks in the ground. So he took his phone and then he started filming because he didn't understand what was happening. And then he saw that the crack was getting bigger and bigger. So what he did is that he ran up the road there, and then he came. There's a see there is a road just below my pointer, and then he ran a bit higher up, and then he started filming again. And when he came up, then he could see that his house was was actually going towards the sea. So the whole thing was sliding down in the fjord. So here we're talking about a landslide that the volume that is approximately 1 million cubic meter. You can see the really the forces that are acting there, and there's a lot of turbulence in the fjord. The houses are really being washed out in the fjord as well. Let's see. So this is quite an amazing video showing how this landslide was occurring. An interesting thing here is that a couple of days before the event, some of the landowners there called actually the government agency in the surroundings because they could see some cracks starting in the ground. And one of the cracks that was registered is probably the start of this deep progressive failure that was going below these houses. So there was a commission that looked into the cause of this landslide in the aftermath to understand what happened. And what we found out is that, again, the person that filmed this event actually, to construct his houses back in 2015, he made he placed a fill for the basement of his house, and that fill was led to a reduction in the safety factor of for more than 7%, and that was enough to bring the slope very close to failure. So back in 2020, in June 3rd, 2020, it had been, that was in Norway, the winter is very late, and at the end of May, beginning of June, there's still a lot of snow melting in the north like that. So you had a lot of high pore pressures in the ground, a lot of rainfall, and that was enough together with the placement of that field to trigger the landslide. Let's see. The next slide that is very interesting is the most recent one that we had, unfortunately, just before New Year's Eve this year on the 30th of December. That landslide occurred at 4 o'clock in the morning. You can imagine the situation here. You are the day before New Year's Eve. People are sleeping in their houses, and then it's -5-6 degrees, completely dark, and then suddenly some of the houses are just being swept out in the landslide crater. At NGI, we got a phone call at 4:30 in the morning. Some of my colleagues were there a couple of hours after the landslide started, and then it was a bit of I would say it was a large catastrophe, and it was a bit difficult to understand what really happened. It was completely dark again, and it was difficult to see all the damages. But we found out pretty soon that that was a very large landslide, and that there was a lot of people that were taken with this landslide. At the end, 11 person were killed, and more than 1,600 person were evacuated from the surroundings there. after this landslide, there was an investigation commission that was put together in order to, again, to understand what happened there and to try to see what we can do to do better planning for dwellings and houses in the future. This area here actually is a quicklay zone, so we knew about the quicklay, but I think that the risk and the hazards were probably not well understood enough. The commission, they had two things that they are looking at. The first one was the cause for this landslide, the actual trigger and what led to this landslide, and the other part of their work is to look into the present Norwegian regulations, the codes, to see if there are any issues that need to be addressed in the present methodologies. When we in the first report that was published in September, just now, it was pinpointed that the main reason for this landslide was erosion in the creek. Here you have the Olmen farm, and there was a large or an important slope going towards a creek there. And these are pictures that were taken a couple of years back. Where we could clearly see that some of the culverts or water lines were being destroyed, and there was some internal erosions in the ground. There's also a lot of erosion in the creek there. And when we look at LiDAR data over this area, we can see that since 2013, there's been nearly 2 meters of erosion in that creek in vertical direction. So this is quite important, and it has affected the stability of the slope over time. Now, during the fall of 2020, there was, again, intense periods of rainfall, and probably the combination of this rainfall and this erosion led to the initial landslide at Gjerdrum back in December last year. So Gjerdrum, I forgot to mention, but this is only a half an hour drive from Oslo, the main city in Norway. So there's quite a lot of people living in this area. Let's see. These are some pictures that are taken from the landslide area, looking upslope where many of the houses have been destroyed. You can clearly see the main headscarp there that is approximately 11, 12 meter high. And you can see the thick amount of debris there. A couple of months after the landslide, it was already possible to walk on the debris. The clay had sort of dried on the top, and we could walk on it. But the slides car has been very unstable for a long period of time. Some of the work that we do at the moment that we're still working with is to stabilize the headscar and to stabilize some of the houses that are behind there. It's not an easy task to work in this area because you have nearly 8 meters of landslide debris in this crater, and then it's just there's a high strength of the debris on the top, but then it's very, very weak below that. And so if you want to bring some people in there, it's dangerous because there's a lot of instability along the flanks of the landslide scar. And this is I just want to arrange my pointer here to show. Can I show that? This is one of the camera that we have. Let's see, it's not working. Sorry for that. Something wrong with the these are some cameras that we have to look at the landslide activity in the region there when we work close by. So you see, this is an after slide, if you want, that occurred late in August this year. So it's nearly 9 months after the main event. So there's still some retrogression going on. So the work that we do at the moment is to go in with an excavator with a very long arm try to relieve the head wall there, to change the geometry so it's a bit more stable, to ensure that we have a better stability of this head wall, and then we can start working within the landslide area. So what we'll do is we'll put some lime cement columns, we'll put some vertical drains, and then that will be enough to put a berm at the foot of the headscar there in order to stabilize and mitigate the area. But this is a process that takes quite a long time, and we're still this is something that we're still working with here in Norway. I could talk about examples of landslides for many hours. There are many of them in Norway these last years. But what we see is that quite often these are triggered by human activity. We had an example back in Scotland in 2012, a large landslide in sensitive clay that triggered a tsunami wave. That was the landslide was triggered by vibro compaction of a vibro roller there along the shoreline. In Katmarka, close to Trondheim, this landslide here was triggered by blasting vibration back in 2009. We have the example from the Skjeggestad bridge in 2015. There was a small earth field that was put in place by one of the farmers there in order to rearrange a golf course. And it was a very small field, but that was enough to destroy the whole bridge. And then, yes, the Alta landslide that I just discussed about. We have some registered a lot of landslide over the years, so we have a nice database here in Norway that we've used to try to understand how the landslide activity has changed over the years. If we in this figure here, we looked into the amount of landslide or large quickly landslide per year, so the frequency per year for periods of 10 years. So these are different decades from the 1970s until today. If we go back after the Second World War and until the early 70s, the government in Norway was pouring a lot of money for the farming industry to rearrange, to reshape the landscape so that it was easier to farm in Norway. And that led to quite a lot of landslides. And back in '78, as I mentioned, we had this Risa landslide that created quite a lot of noise in Norway. It was captured on video, and then suddenly people became aware of this natural hazard. So what happened after the Risa landslide was that there was a large program that was developed in Norway to map the risk associated to quick clay landslide. And this program, as we can see, led to a lowering of the landslide frequency until approximately 2010. Back in 2010 or 2008, we got this financial crisis, and then the government again is pouring quite a lot of money into transport infrastructure sector for development of highway, roads, railways, and so on. And then what we have is that we have quite a lot of projects going on in the last decades, often a lot of pressure on that projects need to be finished and so on. And this seems to correlate quite a lot with the higher frequency that we see in quickly landslide at the moment. So the question is, how will that be in the future? Some words about the methods that we use for the detection of quicklays in Norway. This is in practice, distinguishing between quick and non-quick clay area is a major challenge that we have in Norway, especially in the whole of Scandinavia. Back in the years in the 60s and 70s, some methods were developed that were pretty rough to assess quite rapidly if we have dealing with soft or sensitive clays. Some of the methods that were developed were these rotary pressure sounding methods and a total sounding method. So these are sort of conventional methods that are with a rig where you push a rod system into the ground. And then these are a pretty rough methods so that if you hit stones or gravels or they won't break. Also, with the total soundings method, you can actually penetrate into bedrock by using flushing and ramming methods. So these are methods that have been used for many years, and we have a good experience with that. But I would say that in the last 20, 30 years, we're making more and more use of cone penetration testing, for example, and especially in many projects, we use quite a lot of core sampling. And the reason that we take a lot of samples is that, again, if I refer to the to definition of quick clay in Norway, it has to be tested in the laboratory to ensure that it is a quick clay, because we need to remold the material and look at its strength. So this is an example from one of the research sites that we have close to Trondheim, where we did some CPTs and some rotary pressure soundings. This is the Tillerflotten site. So at the top, we have a dry crust for the first 2 meters below terrain, and then we have a low to medium sensitive clay down to 7.5 meters, and below that we have very sensitive clays with sensitivity up to 250. So it's a very sensitive clay. When we look at the CPT results, here we have the tip resistance, the sleeve friction, and the pore pressure during penetration. You don't see much difference between the load sensitive clay and the very sensitive clay. A little bit on the sleeve friction, but you don't see much on the U2 parameter either. What we see in sensitive clay usually in Norway is that the BQ parameter, so the pore pressure parameter, is higher than 0.8 and quite often close to 1. So this is a good indication of quick clay. The other thing is that on our CPTs, we have resistivity probes as well. So we call them RCPTs, and we can measure the electrical resistivity in the ground. And we know that there's a big difference between a clay that's been leached from the salts and a clay that is still with salt ions in it, that is still a marine clay. And then based on that, we can also delineate where we can find some sensitive or quick clay. The last log here to the right, this is a log from the rotary pressure soundings, and it shows the force that we're using in order to push the instrument or the screw that you saw on the previous slide at a constant rate. So what we see is that when we are in a very sensitive clay, usually the force to push the instrument through the ground is constant or goes downwards. So based on experience on many years, this instrument is used quite a lot in Norway and Scandinavia to try to delineate where we can find sensitive clays. I think that is quite interesting now in Norway is that we have this national database for ground investigation. So this is something that is available on the internet for everyone, and it ensures sharing and reuse of ground surveys in Norway. This is a good basis for assessing ground conditions and leads to very large saving for society, especially important when we deal with the emergency and crisis management. So if you get to Gjerdrum when the landslide is happening, you wonder, okay, which houses should we evacuate? Well, you can go into Nadag and see if there are some investigation that have been done there in the past, and to see where the what is the amount of quick clay and so on. Other methods that we use quite a lot nowadays in Norway is the use of geophysical methods to map the extent of leach clay. One of these methods is the ERT method, or the electrical resistivity tomography. So where there's a current that is sent into the ground, and you measure you send some current at one place, and then you capture it at one other place with some electrodes, and then you have a measurement of the resistivity or the loss of current in the ground. And then based on that, it is good. This method, again, there's a big difference between what is a marine clay with some salt in the pores and a leach clay that will give you a resistivity between 10 to 100 ohm meters, while the marine clay will be around 1 to 10 ohm meters. We can use this method in order to assess the extent of leach clay pockets, and also it's quite good in order to do in a first stage of an investigation in order to plan where should you put your geotechnical soundings. We do that also from airplanes nowadays or helicopters for very large infrastructure projects. This is quite good for railway projects or, for example, highway projects where you have several kilometers that you need to build on and to detect if there are some sensitive clays and the depth to bedrock and so on. So we use these airborne electromagnetics, and we have some good results with that in the last, I would say, 5, 6, 7 years. Once we have an idea of where the quick clay is, the sensitive clay, and so on, we can go and look into the hazard for a specific area. In Norway, we have at the moment more than 3,000 quick clay zones that have been mapped over the last 20 years, and there's more than 100,000 people living in quick clay area. Historically, more than 1,000 persons have lost their lives due to quick clay landslides. So it's quite an important natural hazard in Norway. The hazard and the risk maps that we have, they are publicly available over the internet. This is the website if you want to go and have a look at. It's an atlas where you can go and actually click on the different zones to see when these zones were evaluated, what the risk, the hazard, and the consequence are, and so on. So this work is very important for aerial planning, for emergency preparedness, and for prioritizing mitigation measures on a national basis. One important thing that we quite often tell the region offices and the communa and so on is that be aware, because quick clay can also occur outside of these zones. And this is something that is a bit difficult to show people sometimes, that even though you have a zone there, you can have some marine clays outside there, but it's just that it hasn't been evaluated yet. So the way we do that in Norway is that we use a semi-quantitative approach in order to assess the risk in one given area. So we use a risk classes in the 3x3 matrix. So we have hazard classes going from low, medium to high, and then the same thing with the consequences, and that gives us the risk. So what we do is that, before I go on, we have the risk is the product of the hazard times the consequences. And when we deal with quick clay, there are different hazards indicators that we will weight, and we sum all of that together, and then we do the same for the consequences. So we can have different consequences that we need to look into, and then we will weight them as well, and then we take the product of that to show the risk in one zone. Example of elements of hazards when we do our analysis are listed here. I just go briefly through them, but experience from earlier sliding in one given area can be can say something about the hazard in the zone, the height of the slope, the poor pressure conditions, the thickness of the quick clay layer, and for example, if we look at human activity, has there been some human activity that will worsen the safety of the slope or improving its safety, for example, in the last year or a couple of years. So we put all of that together, and we have some weights for these elements. These weights were given to the different hazard indicators in the early stage when we build that method. The way it was done is that we want to have 25% of the zones at the end that would land into the high hazard column, 25% in the low hazard one, and then 50% of the zones should land in the medium class. So this is a bit how we thought about when we work with these weights here. Same thing for the consequences. So we look at the potential damage in one zone. So we're looking at the number of dwellings, number of person living in the area, power line, railways, and so on. And we build this matrix together. So then what we produce is that we produce these map of hazard level for a given area with the low, medium, and high hazard. And then we have similar maps at the same site with consequence. And then we make the product of them two, and we get 5 risk classes. So this is a bit the way it works in Norway in order to do the hazard and risk mapping. This is quite often done in a sort of a more regional level, but when we want to build into a quick clay zone, then we have to look properly into the stability and need to, as geotechnical engineers, to look into design parameters. Stability analysis in quick clays area, this is important when planning construction work in a quick clay zone. We need to ensure that adequate safety against slope failure is ensured both for the short and the long-term periods. So we do both drain and undrained analysis. We need to document the most critical profile in a given hazard zone. And we need to look at all types of potential landslide mechanisms. As I mentioned in the beginning, it can be flake type, it can be retrogressive landslide, it can be rotational landslide, and so on. In Norway as well, we use both finite element methods and liquid limited method as well. So both types of methods are used. The requirement for safety in Norway is that a quick clay slope should have a factor of safety of at least 1.4. But it's not always possible to achieve. So we look into trying to improve the safety of a slope. And to do that, we need to look at what are the consequences of a landslide in one given zone. So depending on the hazard in the zone and the consequences in this zone, we can choose between a significant improvement or just a small improvement. The difference here could be if you want to build several houses or an hospital or a main highway. In comparison here, it could be for a small garage for your house or something like that. So an example of how this is used here is that if you have an initial safety factor that is 1.0 and you want to build a highway through this quick clay zone, you'll have to, and you're not able to reach maybe the 1.4, but you will have to increase the safety by 14% or 15% if you have an initial factor of safety of 1.0. And the reason for allowing a factor of safety less than 1.4 is that when we look at the slope presently, it is standing. And this is a confirmation that the slope has a factor of safety that is greater than 1.0. So any improvement will therefore represent a real gain to the present situation. So this is a sort of a simple form of Bayesian updating that we're using. So when we look at now the choice of design parameters, how do we operate to select our parameters? We have, first of all, we will start with to look into the region if there are some available ground investigation results in the region. Look into the quaternary geology map, do a field visit, and we would start planning and performing some in situ and laboratory investigation. For most slopes, we want to have at least 2 total station, or for most zones, I would say. A total station for me means that you have a piezo cone test, you will have some pore pressure measurements, and you would also have taken some samples at 2 locations in the slope or in the zone. So those are some lab experiments that we would do. And then we would interpret the CPT data, get a compare with the lab results, try to establish a characteristic design profile, and then calculate the stability of the slope. When it comes to the evaluation of the strength in the slope, we see that in Norway, quite a lot of the slopes that we have, they have a good safety for a drain failure, but the problem often is for undrained or short-term loading. So we use quite a lot of time to try to assess the undrained shear strength of the soil. And we see that it takes quite a lot of time, and we need to do some very careful consideration for this. The preferred order or the preferred method to assess the undrained shear strength is in Norway would be to do some triaxial testing on soil samples of very high quality. If we don't have access to that, then we would use CPTU data and then interpret the undrained shear strength based on empirical correlations from high quality samples that we have established in the past. When this is not possible, most of the time this is possible, but when it is not possible, then we would go to more sort of a Jean-Sébastien normalization to look into the strength of the soil. And the last thing that we would use for design would be fall cone test, uniaxial test, and vein shear test. So some of you might react a bit to that. Back in Canada, I know that the vein shear test is used quite a lot, but in Norway, it is a problem with the clays that we have with low plasticity. The vein shear test in situ is not working properly, and we have some shear band problems that develop when we do in situ vein shear test that doesn't give us the real remolded strength of the soil. So it's not conservative tool in Norway. One of the main problem maybe with when we look into samples is that Norwegian clays are very easily disturbed, and we need to look into the quality of the sample. So the mechanical properties of sensitive clays are very affected by sample quality and hence the sampler type. This is an example again from the Tiller site that we have back here in Trondheim, where we took from the same depth. Those are samples that are taken from 14 meters below the terrain. We have some block samples. This is from the Sherbrooke block samples, so 250 millimeter diameter. We have some mini block samples, which are 150 millimeters in diameter. And then we have some more traditional piston samples, 72 millimeters samples. And we tested them on the triaxial apparatus. All of these samples, if we look into sample quality criteria that were developed by Luna and others back in the late 90s, all of these samples here would land into very good to excellent, very high quality. But that doesn't mean that you have the same strength in these samples. Actually, the difference between block sample and piston sample here is nearly 40%. So it's a very large difference that we need to take that into consideration when we look into design criteria and slope stability. We see the same thing if you look at odometer test results. So sample quality is affecting quite a lot the modulus that you're measuring in the lab and also the yield stress. For a given clay as well, when we think into for stability analysis, the undrained shear strength really depends on factors such as rate of loading, the stress path, stress orientation, and so on. And we see that the Norwegian clays show some strength anisotropy. So there's a big difference if you are in the passive zone, the direct zone of a critical slip surface, or in the active zone. So these are some numbers that we usually use in Norway for anisotropy of strength. So we have the strength in compression or active that is larger than the one in direct shear, and larger again than the one in the passive zone. So these are some information that we need to provide into our stability analysis. I'll jump this one. From time to time as well, we need some information about the shear stiffness of the soil, and we gathered over the last years quite a lot of interesting information about the shear stiffness, shear wave velocity, and Gmax of Norwegian clays. These are some examples here from Onsøy back in southeastern Norway, and again from close to Trondheim at the Tiller research site. And for all practical purposes, what we see is that when we compare data from seismic CPT, seismic TMT, or traditional more type of multi-analysis of surface waves, MASW, we obtain very similar results. So this is good news. We've been comparing the Norwegian data to sites in Sweden, and we see that there is quite a big difference actually. This would be all of the Norwegian data together. So we have a range from 100 to 150 at the surface, and then at if we go at 20 meters depth, from 175 to 250 meters per second. And the range of the Norwegian data is shown here. The Swedish data is much lower than that, but this is still marine clays, but this clay is much higher plasticity, has a bit more of organic content in it, and much higher clay content as well. So those are effects that are probably influencing the shear wave velocity there. And also the stress history has quite a lot to say here as well. We had a look also at some Canadian clays, comparing here the Swedish data with the some Canadian data that we have found in the literature. We can see that the Canadian data is close to what is observed in Sweden. So the last part of the presentation is about the post-failure stage. What we do after we have looked into the stability of a slope where quickly is involved. One thing that we need to look into when we do our hazard mapping and risk mapping is to have a look at the retrogression potential and then the runout distance of a potential quickly landslide. Some terminology here. I'm using the example from the Risa landslide that we looked into in the beginning. The retrogression distance here was 1.4 kilometers, and this is a distance that is taken from the foot of the slope going to the escarpment at the end, and then the runout for the Risa landslide was in the lake, and this is the distance again from the slope toe and until the end of the slide debris. Some factors that, one thing is that what we see is that these two elements there, they are proportional to each other. The two processes are somewhat linked. So we see that the runout distance is very proportional to the retrogression length for every landslide. So what we do usually is we try to find out what is the most likely or the worst retrogression distance for a given slope, and based on that we will assess the runout length. Some factors that are affecting the retrogressive process in sensitive clays is the geometry of the quick clay deposit, the potential for remolding the clay, and that depends really on the available energy in the slope and the properties of the clays as well. How easy is it to remold the material? And also the retrogressive process will be dependent on the potential for the slide debris to flow out of the landslide crater. So it depends really, is it a very narrow creek that you have and then all the material will just piled up there, or is it a sort of an open terrain where the debris can flow out and then leave a scar that is unprotected? For the geometry of the quick clay, as I said, this is something that is important into the analysis of the retrogression. So how the quick clay pocket will lie in the slope will affect the type of landslide and also its final dimension. So this is something that is tells us why it is important to do a lot of ground investigation, for example. The type of landslide as well, and the amount of quick clay below the slope is an important factor that is affecting or sort of leading to what type of landslide we will observe. The figure here is showing a ratio of the thickness of quick clay. That would be the orange part here. So it's the thickness of quick clay above a given failure surface. So it's a ratio between the small b there, so the amount of quick clay above a critical failure surface, and the depth at one point along this failure surface. What we see is that for landslide where you have more than 40% of quick clay above the failure surface, we find in Norway that that leads to large flow slides or retrogressive landslides. For events where you have less than 40%, that will lead to flake type landslides or rotational slide. And then we use that in order to say, okay, if that will be just a rotational slide, then the retrogression will be quite small. Whereas if it's up here, then it will be a much larger retrogression. Another important factor in order to assess whether there is a hazard for large retrogression is to look at the remolded strength of the material. The data here is showing data for many Canadian landslides where retrogression was larger than 100 meters, close to 100 meters, or there were no retrogression at all. And we put also the orange dots there. Those are for Norwegian landslides that have a retrogression much larger than 100 meters. And we can clearly see here, we have this is the undrained shear strength, the peak strength, and then this is the remolded strength at the bottom there. And then we have the sensitivity on this, the other axis. There is a threshold here at 1 kPa. And this tells us that at around 1 kilopascal, the remolded strength there will be too large so that the material can flow out of a landslide crater, and over time it will sort of protect the headscar, and there is a lesser chance that you can create a large landslide. So this is a factor that is quite important in this process there. In Norway, when we look at to the estimation of the retrogression distance, we can have a look at empirical relationships. What we do is that we will draw a line from the most critical slip surface throughout the quick clay, and we use this 1 to 15 slope that would probably it will gather 90% of the cases for the retrogression distance. But quite often what we do is that it will be our analysis will be based on ground investigation. If we find that the quick clay pocket will stop somewhere, that will be the longer retrogression distance. So there are different ways to do it. When it comes to the evaluation of the runout distance, what we do is that we will have a look first at what type of landslides we expect in one given area, what type of terrain there is, and then based on correlations between the retrogression and the runout distance here, there's a proportionality there. We will, dependent on the type of terrain, we will select whether the runout distance will be 3 times the retrogression, or 1.5 times, or half of the retrogression. And this will be used directly to delineate these zones on the maps for the runout zones. We are getting pretty far today as well with numerical methods to evaluate runout distance for landslides. The problem is that there are no tools at the moment that can be used directly for quick clay landslide. This is a material that is a bit special, as you've seen in the presentation. The softwares that are available on the market, they've been built mostly for debris flows or for other types of landslides. So they don't work properly. You always have to tweak the parameters in order to fit the observations. So in practice, this is not very good. So what we've been working with in the last years at NGI is a code called BINCLA that uses a Herschel-Buckley rheology type of model in order to assess the runout distance of quick clay. The model I will be showing here is using a yield strength of 30 kPa. So this is close to the underlying shear strength of the clays at the failure depth at Risa, a remolded strength of 0.7. And there's a gamma parameter there that tells a little bit how fast the strength of the material will diminish in the model. So this is an example of when running the model, and we're able to sort of get to a result at the end that is pretty close to what the observation that we have in the lake. Same thing, that the length or the timing of the event is pretty similar to the observation. The landslide back in Rissa was flowing at a velocity of 11 to 13 meters per second, so about 40 to 50 kilometers an hour. So we obtained some of the same velocities in this model. So this is something that we are still continuing to work with, and I think that will be great in the future if we can develop more of these models together with stability analysis in order to present some good hazard and risk maps. In summary, sensitive and quick clays are challenging materials for geotechnical engineers. I think it's nice to work with that, and there's still quite a lot of work to be done. And maybe some of the challenges that need to be assessed in the futures are, again, working more closely into the detection of these sensitive clays. Try to have better ways or methods to assess sample quality and assessment of geotechnical properties. And there's quite a lot of work yet to be done into leading to better assessment of hazard and risk for retrogression and runout as well. As we've seen into the Gjerdrum landslide, that was actually a quick clay zone. But what happened there is that there was some erosion over time, and it was not taken care of. So just having a sort of a static picture of the hazard and risk is not really good. We should have some tools and methodology so that showing that the hazard and risk are developing over time. It's a dynamic process, and it's changing with the different elements. So if you have erosion over time acting at the foot of the slope, then the hazard and the risk should also be changing. And if that would have been available, then maybe we would have saved this catastrophe back in Gjerdrum earlier this year. So with that, I thank you very much, all of you, for attending, and I'm open for questions if there are any. Thank you.
Thank you, John, for your wonderful presentations. Definitely, it's a pretty interesting topic, and it's a complex subject, which really tough to cover within 1 hour period. I have few questions. I'll go through those questions, and if you you have probably 15 minutes of time now.
Yep.
So if you can answer a few of them, that'll be great. Otherwise, the leftover questions, as we typically do, the audience can send it to us, and we'll send you through email. And yeah, and then you can answer back to us.
You can do that. If you have any questions in the aftermath as well, don't hesitate. You can send me an email at jsl@ngi.no, and I'll be happy to answer all of you.
Yeah. So I have a question. First of all, it says it's a little bit different. It says, how different is the salt effect from Suvaka soil in Middle East? Did NGI do any work on Suvaka soil, salt-rich soil?
I am sorry, I don't know these type of soil. Maybe NGI has been involved there, but I don't know about them.
Yeah, no, that's okay. Okay. Move on to the next one, sensitive living. How do you live on sensitive? I think you answered a few of them. You showed that NGI is going to do that, developing those map and have safety map and hazard map. Similar things, I think the Ministry of Quebec also did for some of the regions in Quebec area
Mm,
for developing those safety hazard map,
mm.
um, doing a lot of spending millions of dollars in terms of ground investigation and things like that. So I think that answers some of the question here. It
Yeah,
says, any
I,
example?
I can maybe add a bit about that. I mean, the city I'm living here now in Trondheim, there are approximately 40 quick lay zones in the city, and that has been like that for nearly 15 years now. It was a bit of a problem when we came out with these maps in the beginning. People were afraid about the house pricing and so on, but it hasn't changed much. I must say same thing for insurance policy and so on. But the good thing is that uh, when these maps are published, it's a bit more strict now to if you want to do some new activities, you know, or some new buildings in these regions, and there are some codes to be followed quite strictly. And but if that is done properly, then I think this is a win-win situation for everyone. Yeah.
Yeah, no, okay. The next question is, how do you minimize the disturbance in general?
I guess that refers to sampling. So what we do is that if the larger the samples you get, the better the sample it will be, because then you want to take a sample. Maybe you will test part of the sample in the middle or the core of your sample. But there's a lot of research that is being going on this to look at the sampling, the sampler geometry. You need some thin walls, and you need a good angle for the cutters, and there's a lot of research that has been done in the past for that. But uh, I think that the thinner the walls and the larger the sample, the better the quality will be.
And I think you showed the difference between that block sample and the piston sample, which
Yeah,
shows although they are quite in terms of definition wise, it's a quality sample, but the results is quite varied in terms of peak and the
mm,
strain softening curve, right?
yeah.
So
What we
um,
see is that the sample quality, it's a big problem with clays of low plasticity, especially clays that are maybe a bit coarser. The clays that we have close in the Trondheim region have a lot of silts in them, so it's very difficult to get some good quality samples. If we move to Sweden or closer to southeast or Norway, then the plasticity is a bit higher, the clay content is higher, and then you get less variation between the block samples and piston samples, for example. So again, it depends on the type of clays you're working with.
yeah, I think there is a similar question here, Sherbrooke sample, right? So Sherbrooke sampler,
Yeah.
it's asking whether you guys also have used that or not.
Yeah, that's what we're using. We have the Sherbrooke sampler at NGI. Use it quite a lot. And what happened a few years ago is that the Norwegian University of Science and Technology, the Geotechnical group, they developed a mini Sherbrooke sampler. So it's 150 millimeters instead of 250. So it's a bit easier to use and has been used quite a lot lately. And we had Guy Lefebvre here that developed the Sherbrooke sampler
Yeah,
back in the 70s, 80s back in Quebec. And he was here a couple of years ago and looked at this mini block sampler that we called, and he was really happy about that. Yeah.
yeah. So you're talking about the same thing basically here. Okay, move to the next question. Any example of a quick bandage to stop or temporary restoration? What do you have in the toolbox?
That is when landslide is started. Is that the
Uh,
question?
to stop temporary restoration. I think restoration, I mean, yeah, I believe that it means probably that when something happens, right? Temporary
Mm,
restorations when you want to fix it, right?
mm, mm. Oh, that's a difficult question. It really depends on the site and so on. I've been in cases where you can clearly see that there's a mechanisms going on. So what we've done is that we get there and we do a berm at the foot to protect the foot, and then that helps quite a lot. But if the process is really starting and the landslide is going on, there's not much you can do really. It's something that happens very, very fast,
Yeah,
and it's very difficult to
yeah,
to
it's
put
very
a
difficult. Yeah,
band-aid on it. Yeah.
yeah, I can hear you. Yeah, no, that's right. Next question is, I'll go skip few here, and how do you measure such low unbrain shear strength? I think you have shown one of the Falcon and other steps probably you use for measuring that very low shear strength, or you can
Yeah.
add
So
something.
what we do is that we use this Swedish Falcon in the
Yes.
lab.
Yeah.
So we use the smallest one there in order to measure that strength. But it's
Yeah.
true that when you go down to point 1 kPa, then you're at the boundary of really what you can measure. Yeah.
Yeah. Yeah. No, the same thing we do here in Quebec and Ottawa too. So
Mm.
it's consistent. Um, yeah. What kind of constitutive model do you use in finite element for quick clays? So
Well, we had there's several that will are used in Norway. We have this NGI anisotropy model in Plaxis that is used quite a lot, and it really depends on what the problem at hand here is. But in the case of slope stability, quite often we use more and more limit equilibrium methods in the beginning, and then the other models will be used mostly for other types of geotechnical problems.
so that comes back to the question: how do you account for the strain softening behavior in the limit equilibrium analysis? What strength is used for a target factor of safety of 1.4?
Yeah, so what we do is that if our design criteria is based on block samples of very high quality, we will lower that strength by 15% to account for strain softening behavior. So we will remove the 15%, and then we will also put the anisotropy factors in there. Yeah.
Okay, great. Okay, so that's for the limit equilibrium analysis. Yeah.
Yeah.
Um, it says, do you install any special monitoring system for quick clay, as landslide in quick clay usually occur without any warning sign?
Mm. Well, that's, I mean, if we knew more about that, I guess we would be rich. It's this is very difficult. I mean, we have pore pressure measurements, but then if you look at that, it will be too late if you really something's happen. I think what we need to look at, and what we're being pressing the different government agencies now, is to try to use lidar data uh, to see and to quantify the amount of erosion, for example, in one place, or to see if there has been some landfills that have been put in place without permissions, things like that. The same thing, there is more and more new type of INSAR data, satellite data coming in now. Next year, I think there's an Indian American satellite that will be launched, and they will be measuring some, they call them the and S waves that can go through, see through vegetation, and that could be very helpful to follow up on the erosion processes in creeks and so on. So you could have a sort of a boundary saying that, okay, the slope safety will be very low if you have so much erosion in a zone, or that could be used to prioritize where you want to do some mitigation work.
So I
Uh,
have just a question came to my mind when you were saying that definitely similar to Quebec. I know that Ministry of Quebec and also what you showed in your presentation, there are hazard map produced including all those current conditions. So when you have more additional data available, I think that map can be reassessed and reevaluated based on
exactly.
the risk criteria. Yeah, that will be
Yeah,
good. Okay.
yeah, yeah. But
Uh,
in large construction projects, what we use when we're building in quick clays, I mean, we have more than pore pressure measurements. We have tiltometers and so on to look at the deformation. But then again, I mean, it's a bit difficult to have some good criterias in order to know how much deformation can you allow in your project before you say, oh, okay, now we need to stop that. Because this processes can go pretty fast when you have a progressive failure.
yeah. It says, what constitutive model do you use? I think you answered that question, but it says from strength degrees due to lost chemical bond between particles. So maybe conventional more Coulomb cannot model this process. Do you think that finite element model and limited equilibrium is enough for quickly landslide, since this large strain deformation occurs more focus is given to material point method and similar method or not?
Well, in our case, the limit equilibrium method have worked pretty good. I mean, I haven't seen any historical landslides where we cannot calculate that based on that method. And when we do a back analysis of the Alta landslide or the Gjerdrum landslides or others, we get a safety factor that is 1.0 or very, very close, and without changing really the strength that has been measured in the slope. Uh, these quite often what you need to find is where the initial failure occurred, but then it's very difficult to simulate or to calculate the whole extent of the failure. But as long as you know where the lowest factor safety in the slope is, I think this is good. But there's a lot of work going on with the material point method and other method, and I think this is also very promising. But uh, in practical engineering, I still think that the limit equilibrium method works good enough for these type of clays.
Yeah, when you mean that, I think you are meaning that initial failure, because I know
Yeah.
that we are talking about here, the question probably refers to the large deformations when you're talking about the complete process of the failure, explaining the failure mechanism after your initial failure, all those horst and gravens in our
Yeah.
spread in
Yeah.
Eastern Canada, or the retrogression of the flow slide
Then I agree. Then we cannot use the limit equilibrium method.
exactly. Yeah,
And
yeah,
the model I showed at the end with the Herschel-Buckley
yeah.
rheology and so on, in these runout models, we are telling the model what's the volume of the landslide there, and then it can start just like that. But what we need to do is to link stability with runout
Yes.
together at the end, and then maybe material point method and other type of models would be relevant for that. Yeah.
Yeah, large deformation model using, say,
Mm.
Kaplan-Orellin, Lagrangian, or similar kind of
Yeah.
those model. Yeah. Um, did NGI do any work on runout distance of mine tailings?
We actually have a research project on that at the moment, but I'm not sure if they are focusing on the runout. The person that asked this question can write me an email, and I will connect them with the people working with that if they're interested.
Okay, okay, sure. I think the question will be followed up after with you then.
Mm.
What is the largest and thinnest quick lay layer you have encountered so far, or how thick or how thin can quick lay layer be?
I have seen layers of very, very sensitive clays that are in the region 20 to 30 centimeters. And then the thickness, I mean, it can be several tens of meters, 10, 20, 25, 30 meters. Yeah.
Yeah, yeah, yeah.
But what we see
Uh,
is quite often in nearshore sediments, younger sediments, you have layered uh, sediments, and then you can have thin layers of very sensitive clays.
yeah. Do you have correlation between liquid index, undrained shear strength, and retrogressive failure? I think you have showed that correlation in terms of undrained
Yeah,
shear strength.
what I showed here was some work that I did with Serge Leroy back in Quebec, and also Vikas also was some of his data, and that was showing the undrained shear strength and the remolded strength and the sensitivity. But all of these parameters are linked together with the liquidity index as well.
Yes.
So there are some references for that, and we've looked into that as well. Yeah.
Yeah, I think those landslide books cover those
Yeah.
relationship there. Yeah. We have 1 or 2 more minutes, so I'll take probably 1 or 2 questions, and then the remaining probably will be sent to you.
Hmm.
What soil strength do you assign for triaxial testing for different factor of safety values?
I didn't understand that
I
question.
don't. Yeah, it says what soil strength do you assign from triaxial testing for different factor of safety
Yeah,
values?
we would use the peak strength. So what we do is we do uh, yeah, we will take the peak strength, but then we will reduce that strength with 15% in the
15%
analysis, as I mentioned earlier. Yeah.
for strain softening consideration. Yeah.
Yeah. Yeah.
Okay. Um, why are quick lays of low shear strength even when they are not disturbed? Such as, why are they low shear strength even without remolding? That's probably the formation of the clay. That's probably he is referring to here. Do you
Well,
understand the question?
the shear strength of a quick clay compared to a clay that is not quick and the same origin will be very similar. There's no difference in the peak strength. The difference is in the remolded strength, and hence the sensitivity at the end. So just looking at the peak strength is not enough. It's really what happens during this remolding process that is important. And then for a very quick clay, then it will be very brittle material, and then the strength will fall relatively fast.
Yeah, you mean that the stain softening effect should be
Yeah,
considered as well. Yeah.
yeah.
I'll take one last question probably. What is the activity index of these clays? Any specific evidence for change in soil concentration, including landslide insensitive clay?
Oh, I don't remember my basics geotechnics, the activity there. That's the plasticity and the clay content, isn't it?
Uh,
These clays are very similar to the Canadian clays, actually.
right.
They are of low activity, but this is not something that we look much into when we do these analysis.
Yeah. One last question. I think it's a similar. It says what he meant was the low shear wave velocity, as you showed in your Canadian and the Norwegian data set. Why are they low in undisturbed clay? The shear wave velocity.
Why they are lower in the Canadian and in the Swedish clay than the Norwegian one? I think part of that is due to the stress history. And also most likely because of the plasticity of the clays and the clay content. So
Yeah.
there are different factors that are affecting the stiffness of these clays. Stress history is probably the most important one, and it seems that this is impacting quite a lot, actually. Yeah.
Yeah. I think the majority of the questions I think have been addressed. I think there are a few more questions left over. I think we are almost 1:30, 2 minutes past 1:30. So I'll give a pause here for a few questions that has not been answered. I think that will be sent to you, John,
Yeah.
and you can answer back to the things. And we typically CGS SOS typically collect the questions and typically send to the presenter. So we'll do it on behalf, and you can answer back to us, and then we'll pass to the individual people who requested for those questions. And by saying that, I would like to again thank you for taking some time and for giving the presentation on these interesting and hot topics with the natural hazards and the climate change and all those other things happening around. And again, last but not the least, I would like to also thank all the sponsors for being with us and cooperating with us and helping this organizing this event. And we are looking forward to meeting you all in our next event, which will be in-person Christmas dinner. By that, I'm kind of leaving and signing up here from Toronto, and hope see you all. Thank you again.